All right, you're there in 4.4, right? We're talking about radioactivity and radiation. You read this, right? I sure hope you did, because there's some good complex chemistry going on here in this stuff. So let's define for me first. What does it mean, radioactivity? Like, what does that? There's about 8 different vocab words in this little section. It's only a 3-page section. What is radioactivity? Can you tell me with the raised hand? Yes, ma'am. Okay, spontaneously. What does spontaneous mean? Randomly, does it need something to cause it to emit radiation? No, it's not like a reaction, right? It just does it. Okay? So it's spontaneous. Okay? And it's emitting, you said what? Radiation. Okay, so then radiation is the rays and particles emitted. Okay? Rays and particles. We're going to talk about those today. Right? The different pieces of that. It's what we call a nuclear reaction. And I'll put this up on Schoology for you as well, the video and the notes. Good to write, though. Writing notes is a great way to learn, just so you understand. What is a nuclear reaction? Well, this has got all the answers. I'm looking for somebody else, so I appreciate that. Yes, sir. An actual change in the nucleus, right? So a change in the atom's nucleus. And this is a big deal, right? How does that differ from a chemical or a physical change, is my question to you. We've got this nuclear change, this nuclear reaction. How is it different from a chemical or physical, Sam?
Usually the chemical reaction, the electrons move around, but the nucleus doesn't get affected. The reaction, the nucleus stuff changes.
Did y'all catch that? This is exactly right. In a chemical reaction, the electrons are interacting, right? And they're giving or they're taking or they're sharing, right? What about a physical change? Nothing, right? The atom stays as it is, right? It would just go from a solid to a liquid or a liquid to a gas, right? Or we're just mixing two things together, right, to form a mixture. In a nuclear reaction, we're actually physically, we're changing that nucleus. And remember, what's in the nucleus? Protons and neutrons. Okay? Protons have what charge? Positive. Neutrons have what charge? No charge. Right? What's our negatives? Electrons. Good. Good. Just reviewing. Reviewing. Good, good. Sir?
Protons are positive in the nucleus. Why aren't there flames?
This is a great question. Sam's got it going today. What did he say? Anyone here? Protons are all positive, right? If you take a bunch of positive things and put them together, what happens? Like electrically, if I take a bunch of the positive sides of magnets and put them together, what happens to them? They repel. So Sam said what? Why don't they repel each other? Why do they stay in the nucleus and make this thing we call a nucleus, not just spread out all over the place? Does anybody know the answer to that? I'll be impressed if you do. The neutrons is a good thought. They remember they're just electrically neutral, so they don't really play a significant role. They do a bit, but they're neutral, right? So they don't affect that positive or negative. What do you think, James?
The electrons on the outside are pushing them.
Okay, so you do have some attraction between the protons in the nucleus and the electrons on the outside, but that would actually just draw them together. You know, there's actually some space between. I like where you're going, though. What do you think, Sam?
I heard about like strong forces.
Sam's rolling today. Have you guys heard of the strong nuclear force? Yeah, what? Yeah, this is we're getting into some good particle physics here. Okay? Have you heard of electromagnetism? Yeah, that's what you were talking about, positive, negative, right? Have y'all heard of gravity?
Yeah.
Good. Berkeley hasn't. These are 2 of the 4 fundamental forces in physics. Gravity and electromagnetism. Okay, you're very comfortable with those. Magnets coming together, right? Electricity flowing, that's electromagnetism. There are two others. One is called the strong nuclear force, which its whole purpose is to hold the nucleus together. And the other is the weak nuclear force, which is what we're talking about today, radioactivity. And these pieces moving out. Fantastic questions. Fantastic. If you want to know more about that, come see me in physics. We'll talk much more about that in physics. For us here, we're going to deal with just it in this little bit here today. Sir?
So do you choose whether you take physics or...
You have your choice. Yeah. Yes, you have your choice. Some folks can do both. It just depends on scheduling-wise. But yeah, usually it's a choice. Huh? They're both fantastic. It's different. It's totally different material. Physics is a little more math and a lot more about how things work, more like engineering based. And A&P is, all about the human body, how it works, all the systems, all that. Sir?
You have to take science.
You don't have to. You only need 3 to graduate, but most people do. Most people do. Exactly. All right, let's keep going. So let's talk about radioactive decay. There's 2 different types. And here's what they are. Alpha radiation and beta radiation. Okay? And again, that decay. Can you read me that definition that's on page 122? What does it mean, radioactive decay? Yes, ma'am.
Unstable nuclei lose energy by emitting radiation in a spontaneous process called radioactive decay.
Okay? There's a key word that's in there, and it was the very first one that she read. Unstable. Remember, what atoms want to be is stable, right? That's why they form compounds, because they're more stable as compounds than they are just by themselves. Okay? And radioactive decay is that same thing. It's getting rid of some things to make it more stable. They show you an example of the lady doing a cartwheel here, right? And when she's up in that cartwheel position on her hands, that's less stable, right? And she then moves over into a more stable on her feet, right? If I were to take a book and hold it up like this, are you comfortable this is more unstable up here than down there? Right? This is a bad drop. Didn't land nicely. Right? It's much more stable on the floor than it is up here in the air. There's more potential energy. Much more physics piece for you. Okay? So 2 types. Alpha radiation and beta radiation. And really there is one more, gamma radiation. But these are the 2 big ones we'll talk about today. And how do they know about this? Well, if you look on the bottom of page 123, you see a diagram similar to this one. And what they did is they took a radioactive source material, and they put it inside this lead block. Can anybody tell me why? Well, what's the point of putting in the lead block? What do you think, Chief?
Lead blocks radiation, so they can have it all go at one point.
Cool. It's because radiation just goes bzz, everywhere, right? But in order to focus it and send it all in one direction, you cover it in this lead piece and send it out. When you go get an X-ray, what do they put on you? A little heavy apron thing, right? Yeah. You know what that's made out of? Lead. Why? It blocks it from affecting. Absolutely. In particular, your sex organs, eggs, the sperm. They don't want that to be affected at all. And other pieces are important as well.
What happens
If you have your hips X-rayed?
then they cause?
Right, sure. No, and one X-ray is not going to cause irreversible damage, But they want to minimize that. If you kept hurting your hip and needed continual X-rays, that could be a problem. Yeah, because you're right. They may have positioned a different way that would keep the radiation from going into that area. All right, so they take that radiation, they shoot it out, right? And they send it through this electric field between these 2 magnets, okay? And what you find is it ends up splitting. That you have this particle that goes up toward the positive side, a particle that goes down toward the negative side, and a particle that goes straight through and not affected by the electric field at all. What charge do you think this beta particle has? Has negative. How do you know that?
Because it was attracted to the positive.
It went toward the positive, right? And the alpha particle is going toward the negative, so it must be. Sir?
Beta electrons.
It is. It is. Yeah, absolutely. And alphas are positive. Okay? All right, let's talk how this works. In order to do that, we got to make sure that you remember how to write our isotope formulas. Okay? So, define for me, please, what is alpha radiation? Can you, and again, we're still on page 123, if you're rolling along with me. Alpha radiation, can you define it for me? Well, okay, they just say a radiation that was deflected toward the negatively charged. So what is an alpha particle? Let's see, someone I haven't heard from. What did you say? Well, take a look. This is on page 123. An alpha particle contains what? 2 protons and 2 neutrons. Okay? So what we have going on here, this is radium. By the way, 226, is that atomic number or atomic mass? Atomic mass, okay, because remember that's protons plus neutrons. And this number down here is atomic number, which tells you the number of protons. Also electrons, but protons that we're worried about. Okay? So what happens is this radium is radioactive. It gives off radiation. And what happens is it turns from radium, it turns into radon. Right? That's Rn. It goes from 88 to 86. You see that? And how it does that is by giving off 2 of its protons and 2 of its neutrons. So can you see that this went down by 2? Because it lost 2 protons, right? Can you see that this, one second, went down by 4 because it lost 2 protons and 2 neutrons? Does that make sense? And what an alpha particle is it's a helium. Right? Because something that has 2 protons and 2 neutrons, that is an isotope of helium. It's helium-4. So that's why you'll see your textbook will use both this alpha symbol and the helium symbol.
Does helium have electrons?
It does, but remember we don't really care about them. They would come along with the journey, but we're not too worried about them because we're dealing mostly with protons and neutrons. It's a good question. Why do we not care about electrons? What is too small? Their mass. Their mass. So we're not really concerned about them. We need them to be electrically neutral. That's a good thing, and they react. But for what we're dealing with here, just protons and neutrons. We're good so far. Alpha is pretty straightforward, right? This guy gives off, just spontaneously giving off these alpha particles, which are 2 protons and 2 neutrons together, which is basically a helium-4. Are we cool? Any questions there? All right, so that's the first type of radiation, alpha radiation. And again, that was the one that's going downward toward the negative side because it's a positive, right? 2 protons, 2 neutrons. We're good? Okay, we're going to take a pause. We're going to take a little brain dump for a second. Stand up. Because we're about to get into some funky stuff. So I want you to stand up. No, really, stand up. Some of you are looking a little sleepy. I know you haven't been in a class for a couple of days. So give me some stretching. Up. Stretching way up. Yes, good. Good. Stretching to the side. Good. How about like stretching down? You can go down as far as you want. Little stretching. Cross over. Yes. Other side. Crossing over. Good. Gotta wait. I'm going to move the arms a little bit. Just breaking some jumping jacks and some push-ups, right? No. I'm just teasing. Okay, you're good? You're awake? So I'm telling you, we're going to be moving now. So have a seat. Let's jump into this beta radiation. Okie dokie. Beta radiation. Okay, so they say that beta radiation is a what? A beta particle is what? An electron. Okay, a beta particle is an electron with a -1 charge. Okay, and if you remember back to our little diagram here, those guys got drawn up toward the positive charge, right? Because they are negative. Positive, negative come together. If we look at oh my. Move this whole thing up a little bit. I thought I grouped these, but obviously I didn't. Okay, so a carbon-14, pause. Is carbon-14 the normal kind of carbon? Look in your periodic table, in the very back. What is your normal isotope of carbon? Well, 6 is its atomic number. Carbon-12. Okay, remember, you say that it's mass numbers that you use to say what isotope. So carbon-12 is the normal. So is this a normal kind of carbon? No, I mean, it is normal. It's not abnormal, but it's not what we usually associate with carbon. It's a more special isotope. Okay? And it goes from carbon-14 to nitrogen-14. Now look at nitrogen on your periodic table. Is that the standard isotope for nitrogen? It is. Its mass number is almost exactly 14.007, but pretty close, right? So what it does is it goes from carbon to nitrogen, and in the process it produces one of these beta particles, one of these electrons. Easy, right? B, that's a Greek beta. Yeah. Do you notice something strange, though? So you see how this went from 6 to 7? And you say, wait, you gave off an electron. How did you add another number there? But the atomic masses, these are the same, right? So this is +1, but these are the same. What? Now, your textbook doesn't go into any more detail. Okay, your textbook just says, hey, here it is, beta radiation. You get off an electron, that's all I want you to know. And I'm going to tell you that's all I want you to know. But I want to explain to you why that's the case. In order for us to do that, you have to understand how beta radiation works. Beta decay is taking a neutron and making it into a proton, and also giving off an electron. And you say, whoa, wait, hold on, Mr. S. Are you saying that neutrons can become protons? I say, yeah.
But aren't protons in
No, they're two separate things. They're two separate things.
together?
They're together in the nucleus, but they are two separate things.
But that means that an electron is going to be in the nucleus.
Well, no, this would go off in the electron cloud around the nucleus. You don't know how it can do that? I'm totally blowing Christina's mind. I can see this. She's like, what are you talking about? Did you know that neutrons and protons are made up of things called quarks? Have you ever heard that term before? A quark? We're getting funky now. I know, Bill. We're getting funky. Okay? If you take and you smash a neutron or you smash a proton, the pieces you get are called quarks. There's actually a lot of other pieces, but for our discussion today, we're going to talk about quarks. Oh, no. They smash them all the time. Have you heard of the Large Hadron Collider? This is in Switzerland and France, right on the border. It's this huge tube. It's miles and miles long. And they get these pieces of these little bits of matter going at almost the speed of light. And they smash them together. Ooh, sounds like fun, right? And they want to see what happens. They have these super high-tech cameras, in quotes, cameras, that you can see the trails and things that are left over. Have you heard them talk about my brain is too tired this morning. That's one way that they do Yes. The God particle. Do you know what I'm speaking when I say that? Why can't I come up with his name? It was just a big deal in the news about a year ago. He just won the Nobel Prize because of it. Higgs, thank you. Sam's on point today. Higgs boson. Okay? This was this thing that they had theorized 40, 50 years ago that was present. And they discovered it. They actually found evidence of it in this Hadron Collider, this Large Hadron Collider. There is one that's in Illinois, just right outside where I used to live, but it's much smaller, not nearly as high speed. Okay? So what they say is neutrons and protons are made up of these things called quarks. And these quarks have got these very complex names, things like up quarks and down quarks, and charm quarks, and bottom quarks, and top quarks. They're stupid names, but I didn't name them. These physicists did. Okay? But up and down are what makes up neutrons and protons. Neutrons are 2 downs and 1 up. You with me? Protons are 2 ups and 1 down. What's that? So this is an extra piece that comes off that your book doesn't even talk about. It's another smaller type of boson. I'm not. Don't worry about it. Okay, but this becomes this when one of these quarks goes from an up to a down. It switches. It switches from an up to a down, and that makes it into now a proton. When that happens, it gives off this little W boson, and also produces an electron. This is the final product that your textbook is concerned with. It doesn't necessarily mean you don't have to know all of this. We'll talk about this in physics class. But that's the process. And there's also this little thing called an anti-neutrino. I don't know if you all have heard of neutrinos, but that was in the news. Did you hear when they said that something could go faster than the speed of light? And they're like, oh, we could have like wormholes and time machines. This was about maybe a year, 6 months ago. And they said, no. Because they had one experiment that showed these little neutrinos going faster than light, which is like the cosmic speed limit. You can't go faster than light. Nothing can go faster than light that we know of. But they had this experiment that showed something did, but no, it was wrong. The measurements were wrong. Sir?
So these quarks, they're not actually little pieces. Is this just like a representation, or they're actually pieces inside?
Well, of course, it's a model, just like anything else we've done. But no, like 3 of these things together is what makes up a neutron.
So they're actual, like, literal things.
Sure, right. Yeah. And they, based upon whether they're positive or negative, and I don't want to confuse you too much, whether they're positive or negative determines whether they're up or down. Okay? Yes? Well, remember, this is a proton. Okay? So 2 ups and 1 down. If I remember this correctly, you're testing me because I didn't check on this. I am pretty sure the ups are 1 positive, and these, no, these are like a half negative. I can't remember. I have to look at it. You have to forgive me I'm blanking on you here. But yeah, it's in the charges of them that cause it to be either positive or negative. So the grand total of this is a 1 plus. The grand total of this is a 0. Big picture. Big picture. Let me pull you back out of the weeds, right? The big picture is beta decay takes this from an unstable carbon-14, radioactive carbon, and turns it into a non-radioactive nitrogen. And when doing that, it gives off an electron. Sir?
So basically, just add 1.
Right, exactly. Mass number is staying the same, add 1 to the atomic number. That's exactly right. If you have beta decay, what's happening, mass number is the same, atomic number adds 1. It's absolutely correct. Exactly. Exactly. Sure. I could give you this and say it undergoes beta decay. What would it write? You're going to do that tonight even. Yeah. Well, I was hoping to do it in class. Maybe we'll wait till tomorrow to do it. Okay? Last but not least is gamma radiation. Okay? Last but not least. Don't worry. Okay? This is easy. So here's our uranium. By the way, flip over to page 124. Gamma radiation is simply just high energy radiation. It has no mass or particle. Okay, it's simply just energy. And it's the result, usually it comes along when you have alpha and beta decay. Okay? So you have these other pieces that are being made, but this is kind of the leftover energy that goes along with it. Okay? Yes, ma'am? It can, but it's very tough to do that. That's what an atomic bomb does. It takes a little bit of mass and turns it into a whole bunch of energy. You're correct. So here's our alpha, right? You see the pattern? Right? This loses 2, right? And what does this lose? -4, right? Because remember, it's 4 on top and 2 on the bottom to make my 1 alpha particle. And that also produces 2 of these gamma radiations. Sir?
Gamma ray is like a neutron. Because in this, I don't know, figure 21, the gamma ray stays the same.
Yeah, it's kind of just rolling right through. It's not actually a neutron. It just has no charge because there's no particle associated with it. Okay, it's a good thought. It's a good thought. Alpha, beta, gamma. We cool? Alpha, beta, gamma. Okay, yes, ma'am.
So you have to have like an alpha thing going on to get the gamma ray. 'Cause it's
Yes.
two.
Yes.
So
Yes.
can't that just happen with any of them? Or is it specific?
It's more your radioactive elements that will do this. I suppose theoretically we could make all of them produce some of these things, but it's with your radioactive. On your periodic table, well, this one doesn't show it. Which ones are radioactive and which ones aren't. There are some periodic tables that do show that. Okay? Whew. You guys, you made it. I am not assigning this for you tonight. I want you to finish that other worksheet that you were supposed to work on the last couple of days. But page 124, the last questions on the bottom, that's what we're going to spend some time with tomorrow in class, as well as going over that average atomic mass worksheet. Okay? If you want to get ahead, fantastic. Okay? But if you did not finish that worksheet, then spend your time there. Okay? Maybe you want to review this, go over it one more time, because again, it's a lot of funky stuff. Okay? Adios, my friends. You did well.